Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. I appreciate you joining us here today as we continue our discussion of exponential functions. We did do quite a bit with exponential functions earlier in the year when we were talking about functions in general, and then we spent some time in our last video talking about them a little more specifically, and we're going to elaborate on that just a little bit today. It was a lot of information to cram into one lesson, so we decided to split it in two. So we're just going to pick up where we left off in our last video, and that is this. How do we decide if something is a linear function or an exponential function? How do we decide if it's linear or exponential? And so I've got three tables here, and we just want to look at these for just a moment, and we want to make a decision about whether these are linear functions or whether they're exponential functions. The easiest way to distinguish is to come over here and to look at the f of x column. You'll notice in every table, x is growing by the same amount, starting at 0. But the f of x column has rates of change that are just a little bit varied. So let's look at the rate of change here in this first table. We start off with an 8, and we become a 12. That's a growth of 4. The 12 turns into an 18, which is a growth of 6. And then 18 turns into a 27, which is a growth of 9, and 27 turns into a 40.5, which is a growth of 13.5. Now, at first glance, I can tell you already that this cannot be a linear function. A linear function always has a constant rate of change, a constant rate of change. So if it started off growing by +4, it should grow +4, +4, +4 forever and ever. This does not do that. It has a rate of change that is changing. And so I can assume, since my only choices are linear or exponential, that this must be an example of an exponential function. In order for it to be an exponential function, though, I have to have a constant factor by which I multiply these rates of change so they continually grow by the same amount. 4 times something has to be a 6. Any idea what that is? Well, it's 1.5, 1.5. And of course, 6 times that same number, 1.5, is a 9. And 9 times 1.5 is 13.5. Because we have that constant factor for our rate of change, we know this is going to be exponential. And I can go one step farther, and I can tell you that this is going to be 8 times 1.5 to the x. Now, some of you are probably wondering how I knew that. Well, when I go through here, this says I started off at 8, and then I repeatedly multiplied by 1.5. 8 times 1.5 is 12. 12 times 1.5 is 18. 18 times 1.5 is 27, and 27 times 1.5 is 40.5. You see, that's what this says. This says you start off with an 8, and you multiply by 1.5 over and over again. Remember, the definition of exponent is repeated multiplication. Now, my students sometimes question me, okay, that makes sense, but they say, how did you know this was a 1.5? Now, I could see it just because I recognize the pattern. I've done it often enough that it comes to me pretty naturally. But there is a quick and easy way for you to find this number, and that is to realize that multiplication and division are inverse operations. If I take this final number of 6 and I divide it by 4, it equals 1.5. And in fact, if I take this 9 divided by the number right before it, which was the 6, it's also a 1.5. And 13.5, which is a lot of writing with a mouse, 13.5 divided by 9 is still 1.5. You see, we can find this just by dividing any two numbers in sequence. If it's an exponential function, what should happen when you divide those is they should all come out the same. Exponential function. Let's take a look at this next one. 11 became a 4. Well, that's a growth of 7, or -7 actually. 4 became a -3, which is a -7. 3 turns into a 10, which is down 7 more, and -10 turns into -17, which is also down 7. Notice over here you have this constant rate of change. That makes it linear. And you should remember from our linear unit that in order to write a linear function, you need a starting point this is b, and you need a constant rate of change, which is m. In slope-intercept form, y equals mx plus b. In other words, in this problem, we started at the 11 and we subtracted 7 repeatedly. That's the definition of multiplication, is repeatedly adding or subtracting the same thing. Exponents are repeated multiplication. Multiplication is repeated addition. I've got one more for you. You could probably see pretty quickly what's happening here. This is not growing at a constant rate. Rather, it's growing by an ever-increasing rate. If I want to find what the factor is to give me the exponential function, which of course this is going to be an exponential function, I happen to know it's 1.2, but you could take 1.44 divided by the 1.2, and it would in fact come out as 1.2. 1.728 divided by 1.44 is also 1.2, as is the next one. Since this is exponential, can you figure this function out on your own? Hopefully you can. I have my starting point of 6, and I repeatedly multiply by 1.2. Notice the difference between linear functions and exponential functions. Linear functions always have a starting value and repeated addition. Exponential functions have a starting value and repeated multiplication. Let's look at a few of these. An exponential function g models a relationship in which the dependent variable is multiplied by 1.5 for every 1 unit the independent variable x increases. Graph g when g sub 0 or g of 0 is 4. Now, a couple nice things they did for us. They told us ahead of time this was exponential. It was very nice of them to do that because now we know we're looking for that y equals a b to the x power, where a is our starting point and b is our constant factor. Notice they also tell us the dependent variables multiplied by 1.5 every time. That's helpful. And they give us g of 0 equals 4. Remember, that's fancy function notation just for the coordinate 0, 4. Here's what we can do then. We can go through, we can say, all right, well, here's x, and here's g of x, and we can make a table, 0, 1, 2, 3, 4, and we can plug those values in based on the description that was given to us. We're told that 0 matches to 4, and then we're told that 4 gets multiplied by 1.5 every time x goes up 1. So if I go from 0 to 1, I take that 4 times 1.5 and I get a 6, times 1.5 I get a 9, times 1.5 I get a 13.5, and times 1.5 I get a 20.25. From this information, I should be able to create an exponential function. The most important parts are right here. I started at 4, and I multiply by that 1.5 repeatedly. Can you give the function from that? Hopefully you can. I've got g of x equals 4, that's your starting value, times 1.5 repeatedly. Now, with practice, we should be able to do this just from the description and not have to go through the trouble of making the table, but I want you to at least see the table so that it connects back to what we did earlier. Couple things, if we wanted to graph this, which was the last part of the instructions, we want to keep in mind that this has a plus 0 at the end of it. Plus 0 is important because it tells us where our asymptote is. I don't want to go too much into detail about that because we did cover it when we talked about the vertex form of functions, and you can go back and watch that video if you really want to make sense of that. But for now, suffice it to say that that's going to be our asymptote. I'm then going to go through and I'm going to plot all these coordinates, 0, 4, 1, 6, 2, 9, 0, 4, 1, 6, 2, 9, 3, 13.5, and then the 4, 20.25 is going to be way up here off the graph. So I know probably I'm going to cross the end of my graph right about there. You can see that nice exponential curve we talked about yesterday starting to come into play. I know it's going to continue on down here towards the asymptote, but it's never going to cross the asymptote. For the sake of getting a nice clean graph, I would go ahead and plug in a few points to the left of the y-axis over here on the negative side. So I'm going to plug in negative 1, 2, 3, 4, and negative 5. If I put a negative 1 into this function as x, negative 1 says use the reciprocal of 1.5. Now reciprocals on decimals are tough, but if I realize that 1.5 is just 3 halves, the reciprocal of 3 halves would be 2/3 times 4 is 2.67. If I plugged in a negative 2, that 3 halves would become 2/3 twice. So it'd be 4 times 2/3 times 2/3, which is 1.78. And we'd continue that pattern on. And then we'd plot those points to get our graph. Now, you should notice at this point that curve looks every bit like we said it would. I did try and sketch this with my mouse a little earlier ahead of time, but it is kind of messy, so please forgive me for that. It is difficult to draw those with a mouse. Also notice here at the end, it looks like it flatlines, but it really should continue coming down here, getting closer and closer infinitely. These aren't too bad, right? There again, they like to ask the questions lots of different ways to make sure you fully understand. For example, they'll give you something like this where you compare two exponential functions. If you look at these two, you'll notice that in the function you have a starting value of 1 that gets multiplied by 2 repeatedly. Over here you have a starting value of 4 that gets multiplied by 2 repeatedly. They're asking you to tell the difference. Essentially, when you've got that 4 in front, it makes your entire graph steeper. That should be familiar to you from our study of vertex form of functions, that anytime you put a times a large number in front of a function, it always makes it steeper. So that's what I wrote. I did use the technical term, which is a vertical stretch, to show that it is 4 times as steep. They do ask us to compare the domains and the ranges. You'll remember domain is how far to the right it goes. Both of these go to the right forever and to the left forever, so the domain is all real numbers. And then the range is how far up it goes and how far down it goes. Notice it goes up forever, but it only goes down towards the 0, towards that asymptote, and never crosses it. So the domains and ranges are both the same. Here's a different form of the same type of question. It says the graph below represents a bacterial population, Y, after X days. Write an exponential function that represents the population. Here again, it's nice when they tell us they want us to make an exponential function, so we don't have to figure that out on our own. Should make this a whole lot easier. They then want the domain and the range. That'll be easy enough. And then they ask us to find the population in 12 hours and also in 5 days. Couple interesting things here. You can do this from just the graph without making the table. If you can look at 0, 3, 112, 248, 3, 192, and 4, 768, if you can see how the rate of change is growing, you could do it without the table. Also, you need to be able to find the starting point. I'm going to go ahead and fill in the table just for the sake of discussion. I'm going to use the coordinates that are given here, 0, 3, 112, 248, 3, 192, and 4, 768. Can you see the rate of growth? Well, this is plus 9, plus 36, plus 144, and plus 576. That rate of growth is growing by 4 every time. Again, if you had trouble figuring that out, 36 divided by 9 is 4, 144 divided by 36 is 4, and 576 divided by 144 is 4. From this information, you should be able to create your function. Y equals 3, we started at 3, and we repeatedly multiplied by 4. 3 times 4 is 12, times 4 is 48, times 4 is 192, and we go one step farther than that and do times 4 is 768. That's the answer to part A. Part B asks about the domain and range. Notice the domain on all of these go to the right forever, they go to the left forever. The domain is all real numbers. Notice that the range, it goes up forever, it goes down just to 0, but it never touches 0. So your domain is all x's as long as x is a real number. Your range is all y as long as y is greater than 0. Again, if you're having trouble with the domain and range, you might want to go back and watch the video on functions. Last question, find the population after 12 hours. Please remember that x is given to us in days, which means 12 hours gets plugged in as half a day. So I'm going to take this function, plug 1/2 in for days. Please keep in mind that 4 to a 1/2 is the same as the square root of 4. And of course, the square root of 4 is not going to show up. I think it's the next slide, actually. There you go. Square root of 4 is 2, and 3 times 2 is 6. Over here, 3 times 4 to the 5th power. We've said for 5 days, 4 to the 5th is 1,024. Multiply that by 3, and you get 3,072 bacteria. There's one last slide. I would strongly suggest that you take the time to pause this and try this on your own and then watch so that you can see if you're understanding or not. Again, they've given us a bacterial population, Y, after X days. We're told that after 0 days, there are 100 bacteria. After 1 day, there's 120. They ask us for the function. We should be able to do that without the table, but I'm going to do the table for discussion. They ask us what happens in 6 days, and they ask us to compare this to the bacterial population in the previous slide. Well, let's see. If I wanted to go to the trouble of doing the table, I would say that 0 days is 100, 1 day is 120. We're looking for how much it changes. Now, ordinarily, we would not be able to tell if this is linear or exponential with just this much information. We really need at least one more coordinate so we could see if it's adding 20 every time or if it's multiplying. But because they were so kind as to tell us they wanted an exponential model, we don't have to worry about that. We can assume that this is just going to be multiplication. Can you tell what you had to multiply by to go from 100 to 120? Hopefully you realized it was times 1.2, which means your function is start at 100 and multiply by 1.2 over and over again. That's part A. Part B says what happens in 6 days? Well, in 6 days you get 1.2 to the 6th power, which is 2.986, times 100 is 298.6, which is about 299 bacteria. Last question, how does this compare to the previous bacteria population? Well, in the previous model we said the function was 3 times 4 to the x. So in this one we're just comparing the rates of change. This one has a rate of change of 1.2. The previous one had a rate of change of 4, which means this one is slower, not faster. Hopefully this has been helpful to you as you work your way through these. Hopefully as we've done several different types of examples, you can see how kind of they're all really the same. They're just phrased slightly differently. As always, if this was useful, make sure you leave us a comment in the comment section. Be sure to click like and subscribe and to turn on those notifications so you can follow along with us as we work our way through Algebra 1. We appreciate you taking the time to watch. We wish you all the best. Take care.